All right, welcome back, everybody. We are going to go through the, I think, machine learning from Kaggle, the learning section. I think it's part five right now from me. Now we are going to discuss about the last session. I think we are discussing about the model validation. Right. So we have this training model already being trained, and then we want to verify whether it's good enough or not. So we validate by splitting the data into two categories, which are the train file and the test file, right? And using the test file, we want to put that test x and y, the input and the output, into the prediction. So we call the dot predict method into the model, and then we want to measure how good is the prediction as compared to the target, right? And how to measure about that is one of the ways to measure is using called algorithm mean absolute error, right? So this one, mean absolute error, and which we import from the sklearn.metrics, which basically you kind of subtract between the prediction and the real output. In this case, we are trying to predict the sale price of the home in, I think, in Iowa, if I'm not mistaken, right? So we know, for example, we take like I don't know, hundreds or the first 20 data from the sale price of the home in Iowa, the real historical data of the home price, let's say 100,000, 250, 1 million, and then we also have the prediction using the model that's already being built, right, by the historical data. Uh, and the prediction, how we got the prediction is we split. Remember, we split uh, the 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 whole historical data basically into two categories. One is the training, and one is the testing, right? And then we use the testing data to get the output of the sales price of so we call it the Y prediction, right? And then we kind of subtract basically the real sale price of the historical data and the prediction, right? And then we absolute it. That means if it's negative, we plus it, and then we average among all of those. Let's say we want to compute the first 20 prediction, right? And so that's why I think it's called mean absolute error, right? Um, so, uh, so that's the idea. So what we're doing right now is to understand more about the idea of there's this term called underfitting and overfitting, right? So again, this is very closely related to how good is our model. Remember, we want to deploy the model in the real world. We are trying to solve a real world problem, right? In this case, we are trying to predict what is the sale price of the house. If given a data, in this case, we use I think seven features that we kind of pick from this example. I forgot what they are, but I think there's like a square footage, whether there's a basement or not. I'm not sure. I might be wrong, right? Whether there's a like swimming pool, whether there's a kitchen, and so on, right? So um, so there's this idea of underfit and overfit, right? So underfitting means basically if your model basically it's too how is it too simple. So remember machine learning or or yeah, I think machine learning in general is basically trying to make a mathematical function, right? Y equals to mx plus b. That's probably the simplest kind of linear mathematical functions from if you remember your high school algebra, right? Computing like the slope or what have you. It's just like a one variable kind of algebra. So if you can think of like y equals to 5x plus 6, for example, that's a mathematical function, right? So if you, for example, you can compute the algorithm or the model, and then you find out that the model is y equals to 5x plus 6. So if you put the x, let's say 10,000 square feet, you put it into the formula, and then you compute the y, right? So in this case, probably because it's you're only using like a 5x plus 6, it's too kind of too simple. So In machine learning, we call that underfitting. Too simple means it's only one parameter, right? So the five instead of like five x plus six, you can say, let's say, if it's more complicated, the formula or the algorithm or the model. See, there's so many words over here in machine learning. You just have to they're all synonyms, right? They're just like trying to confuse you. So don't worry about that. Yeah, basically they have the same meaning, right? Um, so if you want to make it more complicated, which is overfitting, instead of y equals to 5x plus 6, for example, and then it's going to be the formula would be y equals to 5x squared plus 7y or 7, let's say z to the power of 3 plus 10a to the power of 4. So you see there's so many different parameters, right? And it's not just one variable, they're multi-variable. And it's the formula is more complex. It's not simple. So that's the idea of overfitting, right? So if you that's the simplest way I can think of. If you want to think of in terms of mathematical formula, just remember, underfitting means it's a very simple formula, like a linear regression, y equals to mx plus b. Overfitting is a very complex kind of formula, so you can think of the most complex formula you can think of, like multivariable, and then it's using exponential ex to the power of 3, and then even the to the power of is like to the n. It's not just square, it's not just to the power of 3, is to the power of 100, for example. Yeah, it's very complex. So that's the idea of overfitting, right? But if you want to use a different word for this, more like a laid down kind of terms, if you want to talk to like layman terms, right? What is underfitting means? Underfitting means your model is too, I don't know, you can say like it's too general. You are not capturing the real, your model is not capturing the real complexity of the real world, right? Because you only have like one variable to think of, right? So imagine if you want to predict a house and you have a model that says, okay, it's simple. The model is so simple. If you want to predict the sales of the house, all you have to do just input one features, which is the number of bedroom. That's it. So if the number of bedroom, for example, is one, the house price is 100,000. If the number of bedroom is two, the sale price of the house is 200. If the number of a bedroom is three, the sale price is 300,000, right? So it's a very simple, simplistic model, right? But it doesn't work in the real world, right? In the real world, it's much more complex than that. So that's kind of the layman way of explaining it, right? In the same way, if you want to explain what is overfitting, means you can just do the opposite. Instead of your algorithm is too simple, your algorithm is too complex. You are putting too many variables, which probably doesn't need to be there. For example, again, in the determining the home sale price, right? So probably you can think of like if you probably interview a realtor, right? Which already work in industry for like 10 years, 20 years, then they will tell you, oh, what do you think is the determining of the sale price of the house? And they will say, oh, probably the year it was built, uh, how many bedroom there are, whether it has a basement, how many square footage, whether it has an upgraded kitchen, whether it has a second story, whether it's made from bricks, and then one more thing where you can think whether it has, for example, a finished basement, right? So you can think of like, for example, 8 features, right? And this is from like a very experienced kind of a realtor that you can think of in your in your area that you kind of like kind of worship and so on, right? But then your model come up with more than 8 features, right? Probably your model, because it's so complicated, it comes out with probably 100 features. So you can see, right, from 8 features to 100 features. Like for example, you can think of like, oh, how about the number of frog, the number of cows there, the number of cars, the number of public school, which is probably kind of still related, the number of children playing, the number of public park, the number of river. So all of these things that you think it totally doesn't make sense. You just somehow the machine learning captures that somehow. All right. So you can think like from a layman's point of view, oh, that doesn't make sense. Yeah, there's just too many variables there. It I don't think that variable should be there, right? So in that sense, you can say that model is overfitting. Yeah, it's too complex for the real world. So yeah. So anyway, so we are going to um, let's see what's gonna do. So to recap, you already built your first model. Now it's time to optimize the size of the tree to make a better decision. Remember, we are using decision tree algorithm, right, to make a better decision. I think this is kind of the simplest and easiest to understand to learn about machine learning because there's a bunch of plethoras of algorithm out there. There's a random forest, XGBoost, um, deep learning is one of them. Support factor machine, regression. Yeah, there's so many things, right? So and then, so anyway, so run this cell to set up your coding environment where the previous step left off. So we're gonna again import the pandas. Remember, pandas is used for basically data frame, like remember like Excel spreadsheet. So it's basically converting all of your data. For example, you have a data in a .csv file. It's gonna convert it into a nice kind of like a tabular form, like between rows and columns, right? Think about Excel spreadsheet. That's what it's pandas for. I think it's an Excel spreadsheet for machine learning, right? um, we're going to import the way how to compute the difference between the prediction and the real historical output, right? We're using mean absolute error. We're going to import the train test split. This is a library to basically to split the data into two because remember you want to have in order to validate your model you want to have a different uh, uh, data, right? Which is different from the data that you use to train into the model, right? And then we are importing also the decision tree regressor. We already talked about this. This is basically one of the machine learning algorithm. Um, okay, so we did that, and then we are just again, this is just to pointing where the file is, right? So if you can just click this, it should be under so input home data for ML course. It's not here. Somehow it's kind of hidden, right? Um, but you can see here is trying to read the train.csv, right? And then after that, it's gonna read it into the data frame, right? Panda PD, and then we're gonna create the y pointer, which is the sale price, right? And then we're gonna create the x, which in this case we have 7 features, right? So yeah, so 1, 2, 3, 4, 5, 6, and 7, right? And then we're gonna put that features into the x, right, variable, right? And then after that, we're gonna use this algorithm train test split again to split, and we're gonna use a pointer for that two points for that specific data that we already split. So as the input, we put the x, right, which is the all of the features that we want, the pointer that points to that features, right? And then the output, which basically is the pointer to the sale price of that particular data. And then we want it to be reproducible. So we want to use this statement random state equals to something, right? You can use equals to 1, equals to 0, equals to 3. It doesn't matter. I think the variable you can use it until up to 3, right? After we split it and we use a pointer for that specific split data, and we want to specify a model. So we call the model library, and then again we use a random state, yeah, and then this is the name of the pointer to that model. And we want to train it, so um, we call the model, which is the Iowa model, right? Which points to this algorithm because we want to use this kind of algorithm, decision tree algorithm. We call fit, which is one of the methods in um, under this algorithm, right? and we want to what to fit, right? We want to train it. So first we have to put all the training data into the process. So what we want is to put the train X, this one, and the train Y, right? Yeah. So the train X basically is a pointer where the data is pointing to the inputs, right? Um, uh, that correspond to the all of the features, which is this one, the 7 features, right? The Y is also it's a pointer that only pointing to the output for that are being used for the training purpose, right? Okay, so we're done with that. So we already create, once we run this model, we basically create the algorithm, right? Whether the algorithm is going to be simple or not, we do not know, right? Whether the algorithm is going to be underfit or overfit, we do not know, right? But we already created something. You can think of like, okay, I already created, for example, y equals to 5x squared plus 5a to the power of 3 plus e to the power of z plus 6, for example. For example, you can think of that's the mathematical function that the model already generates, right? So, and then so we use that model, we use that mathematical functions to predict, right? So to predict, we are calling the validation data, right? Not the training data. We are using a different set of data. In this case, we call it val slash x or validation x, right? Uh, we're just inputting the x because we want to predict the y, right? So after we call it, right? So this become the val predictions y, right? The output, the sales output, but it's predicted using the model. And we want to compute the difference, the mean absolute error to be precise, right? So what do? We are comparing between, remember when we're comparing the difference, we are comparing between the two variables, which is the predictions and the value y. If you kind of interchange this, I don't think it matters, right? Because you're gonna absolute it at the end of the day. So it doesn't matter if you interchange this. And then after that, you're gonna print the validation MAE, right? With this statement. And this is just kind of for the checking, right? Whether um, uh, it's all just being set up, right? It is input binder. Yeah. Okay. So after we run this, I'm just gonna run this one more time. So we have about what 29,653 mean absolute error, right? So now we are getting into the exercise. So we can write the function of get mean absolute error of by yourself. For now, we'll supply it. So this is the same function you read about the previous lesson. Just run the cell below. So if you want to see the kind of the previous session, this is kind of um, the previous session. Yeah, I think this one. Yeah. Oh no. Well, let me see. Okay, it's over here. Introduction to machine learning. So this is the scientist Dan Becker. Thank you, Dan, for doing this. Um, and then where was I? Oh, here. Underfitting and overfitting. Okay, so you just if you want to learn more, then you just click that one, and then this kind of essays or like you know it's kind of like explaining in more detail, right? So if you still understand what I'm talking about here. So anyway, we are building a function, right? So def is a Python word to create a new function, basically. I think define, right? So and the name of the function is get mean square error, and the parameters that are going to be used are this one. So there's max leaf nodes, train x, validation x, train y, validation y, and then inside that function, this is what is going to be processing or computing. So we are going to process the calling the decision tree regressor, and we're gonna use the maximum leaf nodes equals to maximum leaf nodes, right? The maximum leaf nodes is basically refers to the leaf is because we are using a decision tree. So for example, this decision tree, right? So there are one split. This is the first split, right? And then this is the second split, right? So um, over here is saying for two splits you have um, four leaves. So one, two, three, four. So the leaf is basically um, the predictions, the output predictions, right? So it says here in practice it's not uncommon for three to have 10 splits. So okay, so if we have keep doubling the number of groups by adding more splits, we'll have 2 to the power of 10 groups of houses by the time we get to the 10 level. That's 1,204 leaves. So in this case is you just has so 2 to the power of 10, that's to the power of n. N is the number of split, right? So this one has two splits. So this is the first split over here, and this is the second split. So 2 to the power of 2 is 4, which is that's why we have four leaves, right? One, two, three, four. So leaf, you can think of leaf as the number of predicted uh, output uh, there are. So it's called leaf because basically because it's a decision tree, right? So this is like the roots or the tree, and then you have the branches, and then at the end you have the leaf, right? So that's the idea. And then after that, um, after putting the maximum leaf nodes, so basically the idea here you can choose like how many leaf you want to have, right? So the idea if the more split you have or the more number of leaf, let's say this one is 4 as compared to for example if you want like have 10 split and then you have 1024, which means your algorithm is more complex, right? um, um, because you are asking a lot more questions, right? So over here you're just asking like another like kind of like two kind of questions, like the number of bedrooms, if it's more than two, yes, no, or no, yes, and then how big it is. So the lot size, is it bigger than 8,500 or larger than 11,500? So basically that's like the only variables you're asking, right? So in this case, if you want to use this as a model, probably your model would be yes, underfitting, right? Because it's kind of simple, right? Who would believe that the price of the house is only depending on these two variables, which is the number of square feet and the number of bedroom? Nobody. I don't know. I wouldn't believe it, right? If I have the model that is too simple like this, I wouldn't trust it. Do you? Do you? Do you? Do you? Do you? I don't know. I wouldn't. So you want to have to ask more questions, right? Like again, like if there's a basement, how big is the basement? If there's a swimming pool, if there's a kitchen, how big is the kitchen? If there is upgraded like it's made from bricks, if there's a probably number of public school in the nearby, if there's number of parks in the nearby, and so on. There's so many factors that could be like influencing the price of the house, right? So it couldn't be this simple. Again, if you use this simple, that's the idea, right? So you are trying to compare, you're trying to put like the number of leaves, right? You can change it, right? For example, here, anyway, you'll see later, like between like 2, 4, 10, like two to the power of n. Then the more the more you have n, the more you have split, then the more complex the model would be, right? The more complex the decision tree would be, and then that would tend to be more. The more complex it is, the more overfit. There you go. You got this. I have trust on you. I believe in you. I'm so proud of you right now. I know you can pass this machine learning. It's so easy. You can do it. You just have to keep on like rehearsing it, and try to understand it to the T. That's the idea, to the T. Um, just do one thing really, really well, right? And then you go from there. Um, so after you're putting a bunch of leaf nodes, right? Uh, by determining the maximum leaf nodes, and then you want to you're calling the fit. You want to train it, um, right? Um, by calling the x and y, and then you want to predict the same process by calling the validation x. Remember, using different data to predict, and then you want to compute how error, right? How good is your model is, right? So you're using mean absolute error to help you with that, to determine that. So basically, you're comparing the validation y, right, and the prediction validation that comes out from here, right? The validation y is basically the real historical output sale price of the house, right? And then you return, right? So this is like kind of the structure of this function. Um, so now we are going to step one, different comparing different tree sizes. Okay, how do I do it? So write a loop that tries the following values for max leaf nodes from a set of possible values. Call the get MAE function on its value. So I'm just gonna run this, right? Run this, and then so we're calling the get MAE function on its value. Store the output in some way that allows you to select the value of max leaf nodes that gives the most accurate model on your data. Okay. So this is the candidate for the maximum leaf nodes. So you have 5, 25, 50, 100, 250, 500. So you are going to find a loop to find the ideal tree size. Okay. Hmm. So what is the ideal tree size? That's the question we need to answer. The ideal tree size, I think you have to find the smallest MAE, right? Right, among these three. So you're gonna and then you're gonna store the best value of max leaf needs. Okay, okay. So I'm just gonna cheat. See if there's a solution from here. Um, yeah. So I'm just gonna use this, right? Yeah. So I don't like to think if somebody already like solve it. So okay. So I'm just gonna okay. Let's see. For max leaf nodes in my MAE get MAE. Um, print. Okay. Let's see if this will print. I'm just gonna okay. So it will print that one, right? But um, over here you want to put let's see. So you missed the 25, right? And then there's 50, and then you missed the 100, and then 250, and then 500, and you don't have the 5,000, right? Okay. Let's run that again. So you have the MA over here. You can see which one is the lowest. So this is the lowest. So this should be the best, right? By having 100. So you can see this the model is too kind of too simple, right? Only 5 leaf nodes, right? Over here the model is too complex. You have 500 leaf nodes, right? And this is kind of the one in between. But how do you see it? By computing the mean absolute error, and you can see you pick the one that has the minimum value, right? Because you want kind of the minimum error, right? Because this is all of the error bunch up together and then you average it, right? So 272,000, right? So okay, so now you want to so write a loop that tries the following values for max from a set possible. Call the getMA function for each value of max leaf nodes. We already did that. And store the output in some way that allows you to select the value that gives the most accurate model. Okay, so we want um, how do you store the value? My MA. Probably you can do. How about if it's like this? How do you? Can you do like print best? I'm not really good with this thing, so I'm just gonna try a couple of things. Here I want to see. So it's 294. Oh, so it's creating the it's storing the last one. Okay, got it. Um, how do you store the how do you store the value then? Hmm. How do you store it? Over here is 500 is the optimal because it's the smallest, right? Um, can you like no, because it's just the um probably you can like best 3 equals to um how do I do that? How do you choose like can you do this? Can you do that? No, it's error. Object is not iterable. There should be a function that store that. I'm just gonna use the hint. Um, you will call a getArray in the loop. You need to map the names of your data sets to the names in get to map. Okay, okay. Let me see. Um, map. What do you mean map? I don't know what map does. I don't know. I give up. I'm just gonna look at the solution. I'm cheating. Okay. Oh, oh, okay. This is how you do it. Okay. Leaf size in candidate max leaf nodes. Hmm. Okay. Is that how you do it? Is that how you do it? Okay. I'm kind of confused with this. Okay, let's do this. Like that. Oh, just like that. Okay. Oh wow. Okay. So I can just print best tree size. Oh no. Oh no. No no. Okay, 100. Okay. Okay. So it's for leaf size and candidate. Okay. Scores equals scores get. Hmm. What is the score here? Oh, okay. Score is getting this. Okay. Scores dot get. Hmm. How about scores dot get? Okay. Interesting. I never used this kind of instruction in Python. So I guess so the score is equals to this guy. Okay. Leaf size to the ratio of the get MAE, the mean absolute error. Okay. And then the mean absolute error is you're basically using this where is that? This function, right? So you have the leaf size, trend x, validation x, trend y, validation y, which is this guy, right? So you're calling this function and then passing that parameters, right? These parameters into the function, right? Uh, and for leaf size is um, in that ratio. So in that number. So the leaf size is in this number, right? So from 5, 25, 50, 100. So you put it there, all the leaf size, the train X, the validation X, train Y, validation Y. Yeah, and so you got everything inside. So you got the train X, validation X is from here, right? Again, um, right? So you got this is from here, right? From the train test split, right? And then you put that correspond to the leaf size, right? after computing that. So you got all of these things, right? If the leaf size is 5, this is the mean absolute error, right? Um, if the leaf size is 25, this is the mean absolute error, right? So you got all of that, the ratio, and then all you have to do just use this function minimum, um, choose the minimum, and then you kind of use this key scores that get, and then when you print it, then you get that thing. For example, if you um, so let's say if I print uh, best tree size. Okay, so you kind of print the minimum, which is 100, right? The 100 leaf, which is kind of the minimum of the abs in terms of the mean absolute error, 272, right? What if I can just delete this? Like, what's gonna happen? Hmm, the best tree size is 5. Ah, interesting. Huh, interesting. So it has to be like that. Oh, key. I think it's key, right? Like that. So it gave the 100, which is correct. Okay. So if I don't do this, if we just like it becomes 5. Hmm. So you have to put this in order to really like compute the minimum. Okay. 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 That's kind of weird. This is why I don't like about like it's kind of confusing the syntax sometimes. It's just like, but you get the idea. The most important thing is like the concept. The syntax could be like different, for Python, different for JavaScript, is different for like um. So and I don't like to be honest to memorize all the syntax, right? But the most important thing, you understand the concept, right? Okay, so that's good. And then step 2, we are going to fit the model using all the data. So we know already now the best tree size, right? The best tree size is using 100 leaf as a parameter for the decision tree, right? So right? So we use 100, right? For this is 100, right? And then we want to be reproducible. So that's good. So we know that. So we are gonna implement that into our training the model, right? So we know the best results. If you're going to deploy this model in practice, you would make it even more accurate by using all of the data and keeping that tree size, right? That is, you don't need to hold out the validation data now that you have made all your modeling decision. I'm not sure what it means. Okay, let's move on. So we're gonna fill in the argument to make optimal size and uncomment. So here, uncomment that decision tree regressor. What is the argument? Um, this one. This is the argument. Just copy it and then you're gonna put it here, and then you're gonna put 100 because you know that's the answer, right? The best kind of the optimum kind of a leaf, um, which doesn't underfit and it doesn't overfit, right? You want the model to be the best that you can deploy in the real world, and then don't forget to make it reproducible. Okay, and then you're gonna fit the final model. So we're gonna uncomment the next two line, comment this, just make it go there, and then we're gonna fit. So we're gonna fit this final model, right? We're calling the dot fit method, and then when we fit, we always use x slash train, right? Because we're training the model right now, so we are using the training data instead of the testing data, right? And then we're using the y train, right? Y train, correct? Let me check, just to double check. Yeah, so train x, train y. Oh, so we're not using uh, all capital letter. Just oh, it's a it's the opposite. So train x and train y. Okay, and we're gonna check it. We run it. Incorrect. Hmm. Okay, what's wrong with this? What's wrong with this? It's the same. It's the same. I don't know why it doesn't. Um, just go to the solution. It's quicker. Oh, only x and y? Oh. 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 I got it. So you are not using the. Okay, so you're using basically the whole data. Oh, this one. Okay, you're not splitting it anymore because you know already what is the optimum model, right? What is the optimal mathematical function? Like how many parameters you have to use, whether it's an x square plus x to the power of 3 or you're just using x square, for example, right? So in this sense, because you already know the reason why you need to split up the data into training and tests, right? Um, because you're not sure whether your model is too simple or too complex. In other words, whether your model is underfit or overfit, whether your model is too simple for the real world or is too complex for the real world, right? So you split the data into two, right? But once you know which one is the optimal model, you don't have to split it again. Okay, that makes sense. Okay, okay, that makes sense. So okay, so I know what it means. Okay, so um over here. So okay, so yeah, okay, so fit model using all data. So okay, this is what it means using all data, right? You're not splitting the data into two two separate category. We just train and test. Got it. Because you know already the optimal model. You know the best tree size, or you know kind of the best mathematical function that you can think of, right? Okay. If you were going to deploy this model in practice, you would make it even more accurate by using all of the data and keeping that tree size. Okay, because you want to use also all of the data. Because when you split, remember, when you split the data into two, basically you only have a portion of the data, which means not all. Which means if it's not all, it could be not as accurate. Because remember, machine learning, I think in general, for rule of thumb, the more data you have, the more historical data you have. For example, instead of 1 year, you have like 10 years, or instead of 10 years, you have 100 years. Uh, the more kind of like probability it's higher that your model is going to be accurate because you have more data to train it. It's like think it of this way, like when you when you're a baby, right? Or when you're like right now, when you're the expression of practice makes a perfect, right? The more practice you make, the more you are better at it, right? So think of it like but practice you need more data, right? It's like the data that you need, right? So so the same thing as machine learning. The more data you can put, the more historical data you can put, then the more kind of that model can use that data to practice over and over using a different kind of historical data, right? Okay, got it. So that is you don't need to hold out the validation data now. Okay, so I know what it means, that you have made all your modeling decisions. Okay, got it. This one only applies if you already know kind of the most optimum mathematical function or the most optimum like model, right, for your data because you're already like uh, um, comparing it using the mean absolute error using this tool to know which one is kind of has the lowest error, right? And then we pick that lowest error and then we associated it. Okay, for that lowest error, what is the parameter? In this case, we know the parameter is using the maximum leaf node is 100 instead of like 50, instead of 25, instead of 250. Okay, so now you're using all of the training data, all of the training output, right? Instead of splitting it into two. Okay. Okay. Cool. Okay. That's cool. Thanks you for listening. Let's continue next time. Leave any questions so far. There's no stupid question, just any questions. I'll do my best to answer it. All right. See you next time. Bye. Ciao.